Hello, my name is Junwei, a PhD student in Nanyang Technological University of Singapore. I'm glad to share our new research on distributed active noise control, which is a practical distributed active noise control algorithm overcoming communication restrictions. First, let's see some background. Distributed multi-channel active noise control can assign massive computational effort of traditional multi-channel ANC to several nodes, where each node consists of a controller, a secondary source, and an error sensor. It can achieve satisfactory global noise reduction with low computational costs by exchanging information between nodes. Current DMC ANC just simply apply the distributed algorithm on the ANC system, where each node only updates its local control filter based on its own error signal. The nodes then exchange their local control filters with each other to generate global control filters using topology-based combination rules. However, they rarely consider the crosstalk phenomenon, where other nodes' generated signals affect current node's error signal, as well as communication restrictions between nodes, such as delays and interruptions. They will all degrade control performance and system ability. So we propose a method to solve such problems. As mentioned before, the effect of crosstalk is mainly due to interference from secondary sound sources at other nodes to the current node. These source signals or control signals are all generated by the same reference signal passing through the control filter of its own node. Although it is possible to generate the control signal, which is generated by other nodes by exchanging the control filter coefficients using the idea of distribution. These signals are passed through different secondary passes, which is the secondary source to the error sensor. Therefore, we introduce compensation filters to compensate for the difference between cross-secondary paths and the self-secondary paths, resulting in eliminate interference from other secondary sources. The FX-LMS algorithm is used to obtain these filters. Then, these compensation filters are used to combine the local control filter of other nodes with that of the current node in order to generate the control signal. The global control filter is thus obtained in this formula, as well as the control signal. In order to minimize the error signal at each node, we define the local cost function as this. Then, its negative gradient in terms of phi kn is used to update the local control filter vector as described here. Overall, in the proposed DMC-ANC system, each node only updates its own local control filter, while those received from other nodes remain unchanged. These local control filters will be combined into a global control filter with the compensation filters, which are used to make up the difference between self and cross-secondary paths. Therefore, it can effectively reduce external noise while suppressing internode crosstalk effect to some extent. Next, we show some simulation results. First, we validate the algorithm. From these results, we can see that the proposed method has comparable performance to the centralized multi-channel FX-LMS algorithm in terms of steady-state noise reduction level and the global control filters. Next, we investigate the proposed DMC-ANC system's tolerance to the network latency. Simulation results demonstrate that the proposed DMC-ANC algorithm can successfully converge even when communication latency reaches 3,000 samples periods, equivalent to 187.5 milliseconds with 16 kHz sampling frequency. And note that the average Wi-Fi network latency is less than 100 milliseconds. Hence, the proposed approach could be realized using a standard wireless communication protocol. Finally, we incorporate the intermediate information exchange mode into the proposed DMC-ANC algorithm to explore how communication interruption affects the system's performance. Here we define such equations. If beta k equals to 1, which means there is a communication with other nodes. If beta k equals to 0, there is no information exchange. We will use the previous received local control filters to obtain the global control filters. The simulation results also shows that the proposed algorithm can accept lower communication frequency to a greater extent while achieving satisfactory steady-state noise reduction performance. Now we give some conclusions. In conclusion, we propose a novel distributed multi-channel active noise control algorithm, which utilizes compensation filters to counteract the crosstalk effect between nodes, while only updating the local control filter based on local error information, resulting in distributing computational effort. With these two mechanisms, it is possible to overcome practical communication issues, such as latency and interruptions, while maintaining steady-state optimal control performance. Accordingly, it is anticipated that this algorithm will be implemented using standard wireless network protocols and a lower communication frequency system. Thanks for your listening. I would be glad to welcome you to attend my poster presentation on the 7th of June at 3:40 in the afternoon.